We hear so much about training these huge AI models, right? The months of work, the mountains of data, but what happens after all that is done? Well, that's where the real show begins. Today, we're diving into this kind of hidden world of AI, the live performance, what the pros call inference.
So imagine you've spent a fortune and just countless hours training your AI. It's basically a genius in a box. But how does it actually do anything? You know? How does it go from being this static file on a server to a dynamic, interactive tool that can answer your questions like right now? That's the big question we're going to unpack.
And the answer is inference. Look, if training is the long, grueling rehearsal, then inference is opening night. It's go time. It's the moment a model takes your prompt and actually produces something useful. This isn't just about math anymore, it's about performance, under pressure, live on stage.
To really get this, let's actually follow a single request on its journey, from the second you hit enter to the moment you get a response back. It's this unbelievably fast trip through a super complex digital supply chain.
You can really think about this journey in three main stages. It starts at your fingertips on the user interface. Then it passes through this secure digital doorway called an API endpoint. And then it, believe it or not, waits patiently in line in something called an inference queue. Every single step is absolutely crucial.
So it all starts right here, on your screen, that user interface, the chat box. It's so much more than that. It's this carefully designed bridge between what you're thinking and the model's logic. Its whole job is to make this incredibly complicated process feel totally simple and intuitive.
Once you send your prompt, it doesn't just, float off into the cloud. No, it gets sent to a very specific network address, an API endpoint. Think of it like the official, secure front door to the AI service. It makes sure your request gets exactly where it needs to go safely.
But what happens when thousands or even millions of people make a request at the exact same time? That is where the inference queue comes in. It's basically a digital velvet rope. It organizes all that chaos into a nice, orderly line so the system can handle each request efficiently without just getting totally overwhelmed.
Okay, so your request is in the system. Now the race begins. Because making an AI feel smart and interactive isn't just about giving the right answer. It's about giving it to you fast. Let's look at some of the engineering magic that makes this happen.
One of the biggest tricks in the book is called batched inference. So instead of handling every single request one by one, the system is smart. It groups similar requests together and processes them all at once. It's kind of like a restaurant seating a party of 8, way more efficient than seating 8 separate people. This is a total game changer for getting the most out of the hardware. Now, when we talk about speed, there are two really different things to consider. On one hand, you've got throughput. That's just raw power. How many requests can the system chew through every second? But just as important is jitter. Jitter is all about consistency. A system with high jitter is unpredictable. Sometimes it's fast, sometimes it's painfully slow. For a good experience, you want low jitter. You want that stable, predictable performance every time.
And when you're watching that response appear on your screen word by word, you're actually seeing the token generation speed in action. It's the pace the AI can think and write. Getting this speed just right is what makes a chatbot feel like you're having a real conversation, not just getting a database dump.
And what about really common questions? Well, the system has a clever shortcut for that. It's called in-memory caching. It basically keeps the answers to frequently asked questions in a super fast memory lane. So if your request is something it's seen before, you get an answer almost instantly, because the AI doesn't have to do all that work again.
So, we've seen the whole digital journey of a prompt, but what kind of machine is actually making all of this happen so fast? Let's go behind the curtain, into the engine room, and look at the seriously powerful hardware that is the backbone of all of this.
Yeah, this stuff is not running on your average computer. AI inference relies on a whole family of specialized chips. You've probably heard of some of them, like GPUs and TPUs. They're all designed for one thing: handling the massive, parallel calculations that AI needs. They're the real muscle behind the magic.
And just to give you a sense of the scale we're talking about, just to load one single large AI model into memory, you might need over 80 gigabytes of specialized VRAM. To put that in perspective, that's way more memory than most high-end gaming PCs have in their entire system. It's just massive. So what happens when a model gets so enormous it won't even fit on one of those monster chips? Well, engineers use this really clever technique called distributed inference. They literally split the model into pieces and spread it across multiple processors, letting them all work together to run one single gigantic AI brain.
And before any of that can happen, the model has to be loaded. This is the warm-up phase, and it's critical. Getting those billions of parameters from a hard drive into that high-speed memory has to be lightning fast, because any delay here means the entire service is down for everyone.
Okay, so the system is up and running, the hardware is humming along, but the job is far from over. The final piece of this whole puzzle is the constant, unseen work of just keeping the service reliable, efficient, and, affordable.
Now here's a really interesting secret. Not every single part of a trained AI model is actually necessary. A lot of the time, they have these redundant parts. It's like digital deadweight that makes the model bigger, slower, and more expensive to run, all without adding much value.
And the solution for this is so cool, it's called model pruning. Engineers can literally go in and strategically trim away these useless parts of the model, kind of like a gardener pruning a tree. What you get is a leaner, faster, and much more cost-effective model that performs pretty much identically.
To keep costs under control, a lot of these services use something called serverless scaling. So instead of paying for a whole fleet of servers to be sitting there on standby 24/7, the resources just spin up automatically the instant they're needed and then disappear when they're not. You literally only pay for what you use.
And finally, none of this just runs on autopilot. There are teams of people constantly monitoring the model, looking at a health dashboard of its vital signs. They track performance, accuracy, and costs to make sure the AI is healthy and to catch any problems long before you or I ever notice them.
This quote from the source material really just nails it. It says, "Inference is where the abstract theory of AI research meets the concrete reality of engineering. It's the bridge that actually makes AI useful in the real world."
And that really leaves us with a final thought to chew on. As these AI models get more and more powerful, more and more complex, we have to ask ourselves, is the hardest part building the next amazing AI, or is it the massive hidden effort it takes just to keep the lights on?